Hello everyone, welcome back to this online class. Today I want us to look at Newton's forward difference interpolation technique. Now we have this question. We are asked to discuss the Newton's forward difference interpolation technique and hence work out the following question. Our question is that a function f of x is tabulated as follows. You can see the table of x and f of x values. In part A, we are asked to construct a difference table for the data. Part B, given that f of x is a polynomial, states its degree. And part C, use Newton's forward difference interpolating polynomial to estimate the values of f of 0.1 and f of 1.3. So, first of all, we are going to derive the Newton's forward difference interpolating polynomial and then use it to answer the questions given below. But first of all, let me explain what I mean by interpolation. What does it mean? So you can write a note here that the word interpolation, let me write interpolation. The word interpolation is simply the process. It is the process of approximating values of f of x, of approximating values of f of x at points which are inside the keyword there is inside a given range of tabular points. A given range of tabular points. Remember, tabular points are the x values. So let's say like here, you see the table that is given. We know the values when x is negative 0.2, x is 0.0, 0.2 in that order. But what if you are asked, what about when x is 0.1? You see, we are not given that from the table, but using this idea of interpolation, we can be able to find the value of f of x when x is 0.1. Similarly, when x is maybe 1.1, because that is between 1.0 and 1.2, you can be able to find the corresponding value of f of x. As long as your x values should range from negative 0.2 to positive 1.4. So values of x with between that interval of negative 0.2 and positive 1.4, you can be able to predict the f of x values. Now, when you go outside that range, you see the range for x values is negative 0.2 to positive 1.4. When you go outside the range, let's say you want when the value of f of x when x is 1.6, you see 1.6 is outside the range. Also, maybe you'll want to know the value of f of x when x is negative 0.4. Again, that is outside the range. In that case, we now don't talk of interpolation, but we call it extrapolation. So the difference between interpolation and extrapolation is that interpolation, you are predicting the values of f of x at points which are inside a given range of tabular points. Extrapolation is predicting the values of f of x at points which are outside a given range of tabular points. So that's the difference between the two. Now, usually, the interpolating polynomial is given by, so interpolating polynomial is this one, Pn of x. It is a polynomial of degree n. That is what we are saying is approximately equal to f of x. So that you see, we need to know the f of x explicitly because we know it is a polynomial. If you're given the data, then you need to come up with a function. That's what you mean by interpolation. And once you know the function, you can use it to predict those values of f of x when you're given some values of x between the extreme values of x. So there's what we call uses of interpolation. There are two uses of interpolation. The first one, I'm not going to write, but I'm just going to mention them. The first use of interpolation is to construct the function f of x. We reconstruct it. We want to know it. What is it explicitly? So you use interpolation to reconstruct the function f of x when it is not given explicitly, but only the values of f of x and all certain order derivatives at certain points are known. So that's the first use of interpolation. Another use of interpolation is to replace the function f of x by the interpolating polynomial Pn of x, so that many common operations such as determination of roots, differentiation, and integration, which are intended for the function f of x, can be applied on the interpolating polynomial Pn of x. You see, once you know the Pn of x, which we are saying is an interpolating polynomial for the function f of x, if I were to differentiate f of x, you only need to differentiate Pn of x. If I were to integrate f of x, all you need to do is to integrate the Pn of x, etc. So let us take note. A note, I'm going to write this down. So write a note, another note, of course. Let me not write, because already we have NB. So I'm just going to write another statement here on the note that this polynomial, which we are calling Pn of x, is an interpolating polynomial of if the values. So you can just write Pn of x is an interpolating polynomial if the values of if the values of Pn of x and or its certain order derivatives coincide with those of f of x, coincide with those of f of x. At one or more tabular points. At one or more tabular points. This is what I mean. We are saying for it to be an interpolating polynomial, then we expect that Pn at xi must be equal to f at xi. They must coincide. Another one is when you differentiate Pn prime at xi must also be equal to f prime at xi. etc. up to the nth order derivatives. We can proceed. Pn, of course, the nth order derivative is written this way at xi is the same as the nth order derivative of f of x at xi. So n ranges from 0 all the way up to I ranges from 0 all the way up to n. So you can say where I is equals to 0, 1, 2, all the way up to n. So there are quite a number of types of interpolation techniques. There's what we call the Newton's interpolation. That's the first one. And under Newton's interpolation, we have three of them. The first one is Newton forward difference interpolation. Another one is Newton's backward difference interpolation. And another one is Newton's divided difference interpolation. So those are the three Newton's interpolation techniques. Another interpolation technique is what we are calling the Lagrange interpolation. So we'll talk about that later. And another one is the method or simply the spline interpolation. That's number 3. Number 4 is Hermite interpolation. Number 5 is the least squares. etc. There are quite a number of interpolation techniques, but for our case, we look at Newton's interpolations and Lagrange interpolation. When we come to Lagrange, we look at the univariate interpolation and the multivariate or simply bivariate interpolation. We'll look at that later. So now back to our topic. Our topic is Newton's forward difference interpolation. What does it entail? So let's go back to that now that we know what interpolation is, what extrapolation is, and what we mean by an interpolating polynomial. So now we write Newton's forward difference, Newton's forward difference interpolation. Now, in this case, for you to use Newton forward difference interpolation, you must ensure that the tabular points, which are the x values, must be uniformly spaced. They must be uniformly spaced. So you can take a note that the tabular points, or what we call the x values, must be uniformly spaced. If the spacing is not uniform, you cannot use Newton's forward difference interpolation technique. So what is the polynomial? For this case, we can derive it. I want us to take note. I want us to recall the forward difference operator operating on Fi. So recall that delta operating on Fi, we define this as Fi plus 1 minus Fi. And this was also written in terms of the shift operator as the shift operating on Fi minus identity operating on Fi, which you could also write as the shift minus identity. That's an operator operating on Fi. And so when I cancel this and this, I am going to get, you can just say therefore, delta is equals to the shift minus identity. But you see, identity is just the same as 1, but identity is just the same as writing 1. So therefore, we can as well say that the shift, if you make the shift the subject, it is simply 1 plus delta. 1 plus delta. This is very important. Remember, we derived this when you are looking at finite difference operators. Now you see we are going to apply it to come up with the Newton forward difference interpolating polynomial. Now, we have that. Now, the interpolating polynomial we have said is the same as Pn of x, which is used to approximate f of x. So, we are going to use this transformation. You can write interpolating polynomial interpolating polynomial. The interpolating polynomial is, we are saying Pn of x, that is the polynomial that will be used to approximate the function f of x explicitly. So I can also bracket this. Now I want us to transform the x values to a new variable, which we are going to call s. So we can write, we define the transformation, our transformation is that x is the same as, not x, but s. I'm going to write s. S is the same as x minus x naught, everything over h. From here, it means that x, if I make it the subject, it is x naught plus h s, or simply sh. Is this still the same? Let me write sh, s times h, which is the same as writing x subscript s. So when we substitute that into the polynomial, the interpolating polynomial, that is Pn of x, what are we going to get? But something I need you to take note of is that this transformation will always transform tabular points into integers. You can comment on it and say that this transformation will transform the tabular points, the x values, into integers. This one here transforms tabular points are the x values. You can write x values into integers. Why are we saying it will transform them into integer? Let me explain why. E.g., I'm just going to give two examples. E.g., if I put x is equals to x naught, what will I get as the value of s? I'm going to get s is equals to x naught minus x naught over h, that is 0 over h, and so that is 0. You see 0 is an integer. What about if I put x is equals to, we can talk of x1, what will happen to s? S will be equal to x1 minus x naught over h, and you see x1 minus x naught is the same as h, so that's h over h, which is 1. Again, that is another integer. What about if I put x is equals to x2? What will I get as the value of s? I'm going to get s is equals to x2 minus x naught over h. You see x2 minus x naught, look at here. If I have this one here, and let's say this is x naught, here we have x1, followed by x2, followed by x3, in that order. The spacing between them is h. So this is h, h, h. So what do you think is x2 minus x naught? It is 2h. Twice of h, 2h, then divide by h, and that is 2, an integer. So that in general, if I put x is equals to xi, we'll get s is equals to xi minus x naught over h, that is h, which is the same as ih over h, and that will give us I. All those are integers. So we have explained why we are saying that if we use that transformation, it will transform our tabular points of the x values in terms or simply into integers. So now let's go back to the interpolating polynomial. We have said that we are replacing where we have x, that will be x naught plus sh, or you can also write that as x subscript s, still the same. Remember, why am I saying it is x subscript s? Remember that when we write x1 is the same as x naught plus h. When we write x2 is the same as x naught plus 2h. And you can see it from this diagram that I've drawn. X3 is the same as x naught plus 3h. So what about x subscript s? That will be the same as x naught plus sh. And that's why you are saying I'm writing it as x subscript s. So having explained those ones, let's go back to our polynomial. So therefore, our polynomial now becomes, I'm going to substitute those x values. So therefore, our interpolating polynomial, which we are saying Pn of x, instead of x, let me just write it, is approximately equal to f of x. Now put where we have x, it is the same as x naught plus sh, which is the same as x subscript s. So what will we get here? This will now give us Pn x naught plus sh is approximately equal to f of x naught plus sh, which you can also write as f of x subscript s, and this can be written as f subscript s. Let me explain why we are saying it is f subscript s. The reason is this one. I told you that you can write a note. We said that when I write f subscript I is the same as f of x I. So when I is s, like this one here, it will be f subscript s. So e.g., whenever we write f naught, it simply means that it is f at x naught. If we write f1, the interpretation is that it is f at x1, etc. etc. So when we have f of xs is the same as f subscript s. Now, f subscript s, how can we express that in terms of the shift operator? So the question is, express f subscript s in terms of the shift operator E operating on f naught. How can you write that? So it will be f subscript s is equals to the shift raised to the power of s operating on f naught. That's what it means. But what is the shift operator? Look at our identity. It is this one here, that where we have the shift operator, it is the same as 1 plus delta. So I'm going to replace that. So this is the same as writing 1 plus delta raised to s operating on f naught. Now I want us to expand that. That's a binomial. Let us expand it and see what we're going to get. I want us to recall the binomial expansion. Recall. We are recalling the binomial expansion. And in binomial expansion, you know that when you have a plus b raised to n is the same as a raised to n, or simply let me write the factorial. It is n combination 0, a raised to n, b raised to 0, plus n combination 1. Remember the combinations and permutations that you did in algebra? Those are the ones we're applying here. So a raised to n minus 1, b raised to 1, plus n combination 2, a raised to n minus 2, b raised to 2, plus so many other terms up to n combination n, a raised to 0, b raised to n. That is the binomial expansion. Now, you know how to compute the combination, so I am going to recall the factorial. Remember how to work out the combination, you have to introduce factorials. So let's replace, you can write here replace. Where we have a, let it be 1. Where we have b, let it be delta. And where we have n, let it be s. You will go back to our expansion so that this expansion can now be written as s combination 0, and that is 1 raised to n times b raised to 0 there's f naught, which I'll write outside the bracket, then plus, no, instead of b, we need to write delta because we are replacing. So this will be delta raised to 0 plus s combination 1, 1 raised to n minus 1, delta raised to 1, plus s combination 2, 1 raised to s minus 2, delta squared. We can go to 3 plus s combination 3, 1 raised to s minus 3, delta cubed, plus so many other terms. And then there's s combination n, 1 raised to s minus n, delta raised to n, then plus other terms in between up to the last one, s combination s, 1 raised to 0, delta raised to s. And remember there was f naught outside. F naught is just a constant. And you know 1 raised to anything is just 1. Now let's compute these combinations. S combination 0 is the same as s factorial over s minus 0 factorial times 0 factorial. That's what we mean by s combination 0. I'll put a bracket here. So that's the first term. And you see 1 raised to n is 1. Delta raised to 0 is 1. So what we have is just s combination 0. What about here? S combination 1 is the same as s factorial over s minus 1 factorial times 1 factorial. There we'll just have delta. The other one will be s factorial. That's s combination 2. Then s minus 2 factorial times 2 factorial. Here we'll have delta squared. When it is combination 3, we'll get s factorial over s minus 3 factorial times 3 factorial. This is delta cubed plus so many other terms. Then what about s combination up to the last one, of course. The last one is s combination s, which is the same as s factorial over s minus s factorial times s factorial. This is delta raised to s, f naught. Because you see, let's compute the one for s combination n. So let me compute this. Of course, we'll have that s factorial over s minus s factorial, then times s factorial. So let's work out these factorials. What are we going to get? Take note that 0 factorial is equals to 1. 1 factorial is also equals to 1. So what will we get? Let us simplify these factorials now. This is what we'll have. It is equal to, here we'll have s factorial. Denominator will give us another s factorial, 0 factorial, which is 1. Then plus s factorial. How else can you write s factorial? It is the same as s times s minus 1 factorial. That's what we mean by s factorial. Then we have another s minus 1 factorial in the denominator times 1 factorial, which is 1. Then there's delta. How else do you write s factorial in terms of s minus 2 factorial? It's the same as s times s minus 1 times s minus 2 factorial. Everything over s minus 2 factorial times 2 factorial, which is just 2. Let's work out the s factorial in terms of s minus 3 factorial. So here, remember this delta squared, which I have not written. So here, this delta squared. The other one is s factorial. Not s factorial, but s. We are breaking it down now. S times s minus 1, s minus 2, s minus 3 factorial. Everything over s minus 3 factorial times 3 factorial delta cubed. There are so many other terms up to now. Here we'll have again s factorial over another s factorial delta raised to s, and there is f naught. Remember I said 0 factorial is 1, so that's why s minus s factorial, that would be 0 factorial, which is 1. So let's now cancel this out. You see this and this will cancel. We have 1. This will cancel with this other one. So we'll have just s times delta. S minus 2 factorial will cancel with this other one. S minus 3 factorial will cancel with this. and then this will cancel with this one. So that what we'll have here, it is the same as 1 plus s times delta plus s minus 1 over 2 factorial delta squared plus s minus 1 s minus 2 over 3 factorial delta cubed plus so many other terms up to the last one is delta raised to s. Remember, in between delta cubed and delta raised to s, there's this term that was having delta raised to n, so it is in between, which was s factorial over s minus n factorial times delta raised to n. So simply s combination n times delta raised to n. And remember, there's f naught here. And now you can open the bracket. You can now open the bracket so that this is what we have. So when I open the bracket, this can as well be written as this is equals to f naught plus s delta f naught plus s minus 1 over 2 factorial delta squared f naught plus s minus 1 s minus 2 over 3 factorial delta cubed f naught plus so many other terms, then plus, remember there was s combination n, which I didn't write, you can include it, delta raised to n operating on f naught plus so many other terms up to the last one, delta raised to s operating on f naught, and that's the last term. So I want us, because you see our polynomial is of degree n, our interpolating polynomial is of degree n. So we are going to truncate those terms up to the nth order term, so that we can get Pn of x. You see, we are saying Pn of x is approximately equal to f of s. They are not equal but approximate because it's an approximating polynomial. It is an interpolating polynomial. It can never be equal to f of s, f subscript s. So that's why we truncate up to the nth order term. So right here, you can write truncating this series after the term involving the nth order forward difference and simplifying, we obtain this formula. So let's write it down here. You're going to write the truncation. So you can write here truncate the series up to you see truncating, you get rid of the other terms. So you can just truncate the series after the term involving, instead of up to, I can just say after the series after the term involving delta raised to n. After the term involving delta raised to n, to get the interpolating polynomial. Interpolating polynomial Pn of x naught plus sh. So that means I'm going to consider only the term from the first term all the way up to this term. Those are the terms I'm going to consider. Let me draw it properly. Consider all the way up to this term. So that's what will give us our interpolating polynomial. You see, we have truncated this. So from here onwards, you truncate. So that means there's what we call the truncation error that we incur as a result of when we are obtaining this polynomial of degree n. So having truncated this our polynomial, so you're saying therefore our p subscript n as a function of x naught plus sh is now given by, so you write the first term all the way up to the term involving delta raised to n. So that it will be f naught plus s delta f naught plus s minus 1 over 2 factorial delta squared f naught plus s minus 1 s minus 2 over 3 factorial delta cubed f naught plus so many other terms up to the last term, which is s combination n delta raised to n operating on f naught. So this one here is a polynomial of degree n in the forward difference operator. And so this polynomial is called Newton's forward difference interpolating polynomial. So I'm going to write that. So you can say this is a polynomial of degree n in the independent variable s, and is called Newton's forward difference interpolating polynomial. Newton's forward difference interpolating polynomial. We can abbreviate this as Newton forward difference interpolating polynomial. That's the abbreviation, NFDIP. Newton's forward difference interpolating polynomial. So it is a polynomial of degree n, of course, as you can see in the variable s. That is our new variable s. Now, I told you because we truncated some terms, there's what we call the truncation error. And how do you get the truncation error? You see, we have truncated from the term from s combination n plus 1. We only went up to combination n. So this s combination n plus 1 all the way up to s combination s. Those are the terms that we have truncated. So you can now be asked to find the truncation error involved in this approximation. It's very important. You can write this, that the truncation error is approximated by, so you can write, let me write in another color, truncation error truncation error. How do we get it? It is the error written as E is approximately equal to S combination n plus 1 delta raised to n plus 1 operating on F naught. Which you can write as, this is the same as writing, this is the same as writing S combination n plus 1 h raised to n plus 1. The nth derivative of that function, not nth but n plus 1th derivative, so that is there's a 1 here, n plus 1th derivative of the function at x naught. That is what the error is approximately equal to. You know the h is the step size of the spacing between the tabular points. F is the function that you have been given, f of x, and you evaluate that as at x naught. Now, there's something you need to take note of. So we'll write a note, NB. Note number 1 is that this interpolating polynomial is used when tabular points, simply x values, are uniformly spaced. So of course I had explained there, but you can say Newton forward difference interpolating polynomial is used when the x values are uniformly spaced. That means the h is a constant value, and it is used to estimate values of f of x at non-tabulated points, which are close to the beginning of the table. It is used to estimate values of f of x at non-tabulated points, which are close to the beginning of the table. The start of the table, the beginning, the start of the table. The keyword there is the start of the beginning of the table. I'm going to explain. You see, when we are talking about forward difference table, I told you that table is read simply along a horizontal, along a line that is sloping downwards. So when the line slopes downwards, it means it starts from somewhere at the beginning of the table. So that's why we are saying this formula has to be used to approximate values of f of x at x values which are very close to the beginning of the table, the start of the table. So that note is very, very important. Now, having explained those concepts and derived the formula for the Newton forward difference interpolating polynomial, let's now see how to answer the question that we were given. We are going to go back to that table and answer those questions. Let me take you back to the table. So this is the table of data. We have the x values and the f of x values. So in the first part, we need to construct the difference table for the data. We also need to state the degree of the polynomial f of x, and also predict f of 0.1 and f of 1.3. So I'll take you down. So this is the finite difference table. Of course, in the first column, we list the x values. The next column is the f of x values. So on the right-hand side of the vertical line, we'll have the differences. So we start with the first order difference, that is delta f. As usual, we are subtracting the next minus the previous. So like here, we'll have 1 minus 1.056. That you can press that in your calculator so that you see what you get. 1 minus 1.056. So that should give us negative 0.056. Again, take 0.384 minus 1. That should give us negative 0.616. Negative 0.616. So proceed with the same subtraction until where we have 6.432 minus 2.344. So proceed with the same subtraction, the next minus the previous, so that you see what you're going to get at the end of it. So these are the values we get under the first order difference column. Let's proceed to the second order difference column. We'll write here delta squared operating on f. So as usual, you subtract negative 0.616 minus negative 0.056. You're going to get negative 0.560. So we write it here, negative 0.560. Again, negative 0.792 minus negative 0.616. That will give us negative 0.176. We write it here, 0.176. So proceed with the same subtraction up to the end. You see what you're going to get. So these are the values under the second order difference column. Let's proceed to the third order difference column. So write here delta cubed operating on f. Again, we subtract as usual. Negative 0.176 minus negative 0.560. That should give us 0.384. Similarly, 0.208 minus negative 0.176. Again, that is 0.384. So let's proceed with the same subtraction up to the end so that we see what we get under that third order difference column. So these are the values we get under the third order difference column. Now, what do you realize? That in this column, the values are the same throughout, 0.384 throughout. So it's a constant figure. And so we cannot proceed. It means if we continue with the subtraction, the next values will just be zeros. So once you reach to a constant figure, there's no need of proceeding with the subtraction. So we stop there. And so this is our finite difference table. Now let's answer part B. We need to know the degree of the polynomial that was used to generate this kind of a table. So we are going to say in part B, you write this, part B, you can say, since the third order differences are equal, let me use this other color. Since the third order differences are equal, are the same or simply equal, comma, the interpolating polynomial must be of degree 3. So you write the interpolating polynomial. Interpolating polynomial must be of degree 3. So degree 3 because we have a constant figure at the third order differences. So this is what we mean that our interpolating polynomial is of degree 3. So it's written as P3 of x. So we can therefore say that our function f of x, which was given in the table, is approximately equal to a polynomial of degree 3, which is P3 of x. Now, what is P3 of x? Let's go back to the Newton forward difference interpolating polynomial of degree n. Now, we replace n by 3 so that we get a polynomial of degree 3. So that we know its general form, the general form of this polynomial. So we are going to write here that the Newton's forward difference polynomial of degree 3 takes the form, because this is part C. So Newton forward difference interpolating polynomial of degree 3 is P3 of x, that is equals to f naught plus s delta f naught plus, now it is s into s minus 1 over 2 factorial delta squared f naught plus s minus 1 s minus 2 over 3 factorial delta cubed f naught, because it is of degree 3, so we reach up to third order term. Now, we said s is the same as s is equals to x minus x naught over h. So h is the spacing between those x values. So our h is, if you look at the spacing, it is 0.2 throughout, because the step size is 0.2. So h is 0.2. We said the spacing between the x values. So let me comment here. The spacing between the x values. Remember, x values are also called tabular points. So let's now use that polynomial to predict f of 0.1 and also f of 1.3. So we start with f of 0.1. We want to predict this. Predict f of 0.1. How will we work it out? So this is what we'll do. You let x to be 0.1. This is our x. So let x be equal to 0.1, so that we now need to get s, because now we know x. Now, what about x naught? Look at our table. This is the x, which is 0.1 that we need to predict. The value here, 0.1. So we need to predict the value of f of x at this point. So we can say our x naught can be 0.0 or even negative 0.2, so long as it is a value of x above 0.1. For this case, let us use 0.0 as our x naught. This is x naught. Or any other value above 0.1. So our x naught will be 0.0. 0.0. So if x naught is 0.0, what is our f naught? Is the value corresponding to x naught, that is 1.00. This will be our f naught. So therefore, we can now be able to calculate S. S will now be equal to x, which is 0.1, minus, so we are getting the value of S to be 0.5. Remember, it was x minus x naught over h. When you substitute, you get 0.5. Now, we already know f naught. We know S. Can we get delta f naught from the table? This one, we can read it from the table. Also, delta squared f naught, you can read from the table. And delta cubed f naught, you can read from the table. So let me go back to the finite difference table. You see this value here. This one is our delta f naught. We said we are reading it from, or simply along a line that is sloping downward. So the line should slope in this direction from f naught in this manner. Let me indicate using another color. This is how you need to read it. It should slope in this manner from f naught going in this direction downwards. So this is delta f naught. Delta f naught. This other value is delta squared f naught. So right here, delta squared f naught. And lastly, this other one is the delta cubed f naught. Delta cubed f naught. So let's substitute f naught, delta squared f naught, delta cubed f naught, and even s into our polynomial of degree 3, the interpolating polynomial. So in this case, our f of 0.1 is approximately equal to P3 of x naught, which is our x naught is 0, plus s, which is 0.5, times h, which is 0.2. So that should give us simply 0.1. So let me just write 0.1 instead of writing all that. So we wrap this, and I write P3 of 0.1. So we substitute here f naught, can refer back to the table. Our f naught is 1. So I'll write here 1 plus s, which is 0.5, times delta f naught, that is negative 0.616, plus another s times s minus 1. So here we have 0.5 into 0.5 minus 1 divided by 2 factorial, that is 2. I just write 2 factorial. Delta squared is negative 0.176. Let me take this to the left. Then we have plus s, which is 0.5. S minus 1, again, that is 0.5 minus 1. S minus 2 is 0.5 minus 2. This is now over 3 factorial. delta cubed, we got 0.384. So you can press this in your calculator. Press the whole of that. Remember, 2 factorial is 2, and 3 factorial is 6. When you press that, you get the value to be 0.738. 0.738. So you can just say that therefore f of 0.1 is approximately equal to 0.738. So do the same to get f of 1.3. So in Roman 2, we'll talk of f of 1.3. We need to estimate or predict, estimate f of 1.3. So in this case, our x is 1.3, is our x. X naught should be a value that is just above 1.3. So you can say here that let x be equal to 1.3. That should be 1.3. What about our x naught? Now let's go back to that table and check any value above 1.3 in the finite difference table. I can locate 1.3 somewhere here. This is 1.3. It must be a value above. Of course, I cannot pick 1.2 because you see when I read along that line sloping downwards, I will not get to third order. So pick a value that will land you up to the third order. So x naught, you can return the same value, which is 0.0, and our x is 1.3, or you could even use 0.8. It's still the same, but let's use 0.0, which return the same value of x naught. Our x naught, we can return this as 0.0, or you could use 0.8, or even any other value. Let me demonstrate with 0.8 so that we see how we can do this. I said any value above is a 1.3, and when you read sloping downwards, should be able to give you those are the higher order differences. So remember here there was a 0.38 for which I didn't write 0.384. I didn't write that. So if this is our x naught, if this is our x naught, in this case now, this other one should be our f naught. F naught. So the value here is delta f naught, because you see we are reading it along the, let me draw the line. This is how we need to read the values. You read along this line. You have to slope downwards. Somebody might ask, why didn't we pick 1.2 or even 1.0? You see, when you pick 1.2 as your x naught, you're going to read only, because that will only give you up to the first order column. The second order column is not there for this value of x naught, and also the third order column is not available for that value of x naught. And I said x naught must, when you pick x naught, you must be able to read all the way from the first order, second order, third order differences. So the value here is delta f naught. Delta f naught. This other value is delta squared f naught. And lastly, this one is delta cubed f naught. So let us now go back to the polynomial with those new values. So we said x naught is 0 point. Instead of 0.0, let's try 0.8. That's what we have said. Or you could also use 0.0. You are going to get the same answer. So we try 0.8. So with this, you can now find the value of s. So you write s is equals to x minus x naught. That's 1.3 minus 0.8 over h, which is 0.2. So press that in a calculator. See what you're going to get. You can be able to simplify that. When you work it out, you need to get 5 over 2, which is 2.5. So this is 5 over 2. And that should give you 2.5. So back to the formula, we substitute s, f naught, and its differences up to the third order difference. So you can now say here that, let me pick this color, that f of 1.3 is approximately equal to P3 of 1.3, which is the same as f naught in this case is, go back to the table and read it. That is negative 0.984. 984. Let me write that properly. 0.984. Then we have s times delta f naught. Our s is 2.5. So right here 2.5. Our delta f naught, we got 0.984. So write it here, 0.984 plus s, which is 2.5. S minus 1 is again 2.5 minus 1 over 2 factorial. Delta squared, that is delta squared of f naught, that was 1.360. So right here 1.360. The other term is plus s, which is 2.5. S minus 1 is 2.5 minus 1. Then s minus 2 again, 2.5 minus 2. So now you divide by 3 factorial times delta cubed f naught, which is 0.384. 0.384. So again, press this in your calculator. What do you get? Just press the way it is. This should be able to give you 4.146. 4.146. So you can just say that therefore f of 1.3, f of 1.3 is approximately equal to, that should be 4.146. So we have estimated that value. And so this is how to use the Newton forward difference interpolating polynomial to be able to estimate values of f of x at corresponding to some values of x within the extreme values of x. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech and you'll find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving forward difference interpolation. Bye-bye.